All right, so
perfect. Thanks, everyone. I'm really sorry I can't be there. I had it all planned, and I'm not there only because I couldn't get a visa to get into Spain. The visa process is extra slow in Chile, and that's the only reason I'm not there. So thanks for listening in. I wanted to take this opportunity, rather than presenting what we want, this is the perfect forum to ask you for what you want in curating ngEHT sources. So this comes from the whole collaboration. There's so many people involved. And the idea then is how do we continue so that we can really be ready for the ngEHT?
So Neil, sorry to interrupt. Can you share the screen? Maybe it's more convenient for you if you have,
okay.
Right? Otherwise I have to change slides. So maybe, please try.
And I'm sharing now.
Much better. Now it's perfect. All right. Thanks.
Okay, perfect. So hence, there's so many people involved. I haven't mentioned anyone. It's really about opening a discussion of how you'd like to continue this. And the whole idea is, of course, that the current model is with a 500 millijansky limit for phasing up ALMA. And even now, if it's 40 millijansky, it's really you identify a feasible sample of a few hundreds of galaxies. And then everyone's forced to design their science around this. And the ngEHT model, of course, is very, very different. There's so many exciting science working groups with their own science goals. And so ideally, they would just create an overpopulated list of sources or parameters that they want to look at. Certain range of black hole masses at certain different bins of redshift and certain different volumetric luminosities or Eddington ratios, or literally a sample list, a source list. They can then go to a database and either explore all of the existing database by parameter, or you can cross-match your source or sample to this database. And so but it's not kind of NED really, because you find your data and this feeds into different kinds of models that you might want. Maybe you want to model the SED, maybe you want to model binary black holes, but effectively in the end, you also want to estimate the AHT flux. And you also want to test and refine your observing strategy. Then in the little experience we've had, we've only, in our last 2 cycles, we've only asked for samples of about 20 to 30 sources, but it's also already clear that we can't manage this by email. We need a broker. So you go through this process and you find that there is missing data. We have a lot of missing redshifts, a lot of missing black hole mass estimates for your favorite sample. You might get an estimate from the SED modeling, but you want to confirm that 230 gigahertz flux before going to the AHT. Or you want to do VLBI fringe tests at lower frequencies to see if the emission is compact. And so hence the idea of, and this is to discuss a little bit later, it would be very useful to have a broker where you put in your requests and then some seller somewhere meet those requests. We also have to have coordinated fringe tests. Otherwise, we'd all be writing little proposals for fringe tests of our favorite sources. And then finally, the observational campaign. So this is the question now to bring up the discussion here is how do we do this? But just for some background, where are we? So currently with Ether, we are just a database and we have some models running on the database. We don't have a broker yet. And so it's starting to get large. We have almost 1 million black hole mass estimates. Only 200 are measurements, as you know. The rest is all sorts of estimates from M sigma, M bulge, reverberation mapping, so-called single epoch reverberation mapping, various fundamental planes. The bulk of it is from SDSS, from M sigma or from single epoch reverberation mapping. But in the future, we'll also have a black hole mapper, which is going to do another 300K. And we want to do a lot of work with foremost and moons here. There's also all of the high resolution VLBI observations, which is just one part of the story. So typical catalogs, lots of astro queries, and then a whole lot of SED data. So all this has been brought into one single database. And our general case, of course, is we want to estimate a 230 gigahertz flux for these. And really, if you look at so here's a spectral energy density, frequency versus nu L nu. And in this case, it's an M87 in a certain model. The data, the actual observed fluxes are here. And what you see is a jet model and an ADAF model. So the jet is the green dotted line, and the ADAF is this purple line, and then the summed flux is also shown. And the whole point is, as everyone knows, M87, of course, is a specific case, but your centimeter waves, a VLBI detection of centimeter waves means you have a jet, but you just have no idea what the millimeter flux will be, because that could also be from the accretion flow, and it probably dominates the jet at 230 gigahertz. So really, we're doing it 3 ways. We're doing the strong VLBI sources at centimeter wave and pushing them up to high frequency to check their 230 gigahertz flux to see they're still observable. we're directly observing 230 gigahertz fluxes of large rings. And actually, the most promising thing for the ngEHT is because we can't cover a lot of sources here. And the standard source your science working group is going to come up with will not have either of these. And we have no large 230 gigahertz surveys. So what we're really working on is modeling from the overall set, especially the hard X-ray and very high energy points, try to model what the 230 gigahertz estimate will be. Why this is extremely promising is because of E Rosita, which will give us 1 million hard X-ray fluxes. If you have a black hole mass estimate and a hard X-ray flux, that could be enough to immediately kind of constrain the accretion inflow flux. And then we'll have to check it with surveys and then go to the EHT. So the one from the left, we're pretty much done. If you go on from the left and look at the bright millimeter wave cores, centimeter wave cores, you can populate, you can start to populate these figures. In this case, I showed the...
Sorry to...
Yeah?
I have a quick question. Is this database searchable by distance?
Yes, yes.
Sources?
So actually, well, right now we built, right now it's command line, but Joaquin Hernandez, who's right now is basically building an Airbnb interface. So you literally go in as if you're an Airbnb, you set your price range, and for us, you could set a mass range. You have a lot of sliding filters on each parameter, and then you have the selection only with swimming pools, which in our case would be only has a VLBI, only the VLBI detections or only the hard X-ray detections. And you can slowly filter out your sample and kind of visualize it and then dump it out to an output FITS file for exploration.
And distance is included as one of the...
Oh, yes.
Okay, great.
Yes. Yeah. So we have, we've got about, oops, it's terrible. We have something like 400 parameters already in, including Eddington ratio. Well, not all of them are populated, of course. As much as we can populate with Eddington ratios and the basic, they're all position matched effectively. So we have all kinds of names, all kinds of positions, distances, redshifts, actual SED data, plus the VLBI data, hard X-ray fluxes, and then the model results when we run these JET plus ADAF models to give you estimates. So you can have an estimate just from a pure Paolo extrapolation from other frequencies or from detailed modeling fits. And how detailed in some sense depends on you. So I think the database, we're kind of done, except, well, not done. We have to make it more efficient. But the contents, I think, are pretty complete already. And where we have to make it better is we're actually lacking a lot of redshifts and black hole mass estimates. So for example, most of the strong VLBI sources still don't have black hole mass estimates. And so we're trying to pursue this. So effectively, if we do it this way and we say, what's the estimated 230 gigahertz flux versus the ring diameter of only VLBI detected sources, you can start to place objects on the map. The colors are not so important. Actually, the colors are EHT detected in red, GMVA detected, 86 gigahertz detections in blue, 43 gigahertz detections in brown, and all the cyan are less than 43 gigahertz. And here Venki and Danya now are working on kind of going up the frequency curve so that we can really check what that 230 gigahertz flux is. And we have these proposals with the EHT. The first one ran in March, and we've now proposed for more to start to eat into these with fringe tests with the EHT plus ALMA and see which are the best sources. So this part, in some sense, we've got our database set up, and what we're missing is redshifts and black hole mass estimates for many of these objects, which we are working on with bespoke proposals, basically to follow these up. You can look at this in many other ways, and I don't want to plot everything against everything, but for example, here you're thinking about binary black holes, binary supermassive black holes. This is the linear resolution of the EHT, full with half max resolution, versus the estimated EHT flux, again, only for VLBI detections. And as you see, the nice thing is we are sub 0.2 parsec across the universe, which is, this very nice region of gravitational wave in spiral. And people, you could start to pick objects from here based on other properties, which could be binary supermassive black holes. And later we can try to model that for you, separating out different mass ratios, different orbits, and different flux ratios to each of the to each of the pair to see what kind of detectability we could get. There's the second part that we are also pretty much in progress. There's not much to say. Is there are a lot of objects which are not detected at centimeter VLBI, but they have very large rings. So I plotted these orange targets here. Yellow targets here. What they are is the y-axis is completely exaggerated only to put them on the plot. We have no idea what their 230 gigahertz flux is in most cases, and they're not centimeter wave detections. But remember that it means they probably don't have strong jets, but that doesn't mean they don't have strong accretion flows. And so that's where all of these missing large rings are, right? There are lots of them here. It's just that they're very weak. And so here we're systematically following them up with ACA proposals. We've done 35. We have another 35 in the queue. We've asked for 110. And we're going to keep going. Now, it's not very, I mean, we just want a few, right? So far, it's not very nice in the sense of here's these same yellow sources, but plotted as a histogram. These are their ring sizes and their numbers. The overall red curve is all of them. The green filled histogram is how many of these have estimated or measured 230 gigahertz fluxes greater than 10 millijanskis. And you see they're just very, very few. And 10 is also is pushing the limit for any kind of ngEHT. Having said that, the blue histogram shows you the ones that we haven't observed yet. So effectively, all we're saying is, yes, very few have 10 millijansky or above, but it's because we don't know their fluxes in most cases. And this is what we're trying to complete right now. We're relatively complete in the higher rings, but as we go down to about 3 microarc seconds, and with errors, they could move up and down, we still haven't observed them yet. Some are in the queue, some have been proposed for, and some will be proposed for. And this, if you just want to look, this is kind of the largest rings, starting with looking at this column here, starting with Sagistan M87, and then there are all these others intrinsically resolvable rings. To be careful, of course, if there's a star against the black hole mass, it means it's a measured black hole mass. So you can trust the ring size. If there's no star, it means an estimated mass, either from M sigma or ML bulge. And we're trying to follow these up to get a slightly better estimate anyway. But you have this whole group of sources here. But if you look at their VLBI fluxes here, or if you look at their directly measured 230 gigahertz fluxes, they're all pretty weak. They're 1600, which is a beautiful target, is less than 1.1 millijanskis in our observations with ALMA. And so you see a few of them pop out, 7.9, 11.7, even at low resolution, or even their VLBI fluxes. But if you go down this list, of course, there are some targets. So as to say there's hope, but we haven't found something brilliant just yet in this highest part here. Of course, we should monitor. So the most promising thing actually is to go in from the right, and this is right now in progress, because as I mentioned, eRosita is going to give us 1 million X-ray fluxes. Black hole mapper is going to follow these up and plans to give us 300,000 black hole mass estimates. So you have hard X-ray flux, you have a black hole mass estimate. You can use all kinds of models, either GRMHD or what we're using right now, the analytic ADAF models from Dominic and Ramesh Narayan, which basically give you 3 components, synchrotron, Compton, and Bremsstrahlung from the accretion inflow. And it only depends on 2 parameters, the accretion rate and the black hole mass. So if you put in a black hole mass, for example, here an M87 black hole mass or Sagitta black hole mass, as you increase the accretion rate, you kind of have this monotonic increase in the X-ray flux. So in some sense, what you're saying is if you believe that the X-ray flux comes from the accretion flow, you put an X-ray flux value here and Earth's flux will be. Of course, this is very simplistic, but we're trying it out. And it does seem to work. Here are just some examples. 4261, which actually we proposed for EHT imaging because it turned out to be very bright in our fringe test in March. It's got an 8 microarc second shadow. So if we can detect it and image it, that's a very, very promising source. The red points are the high resolution data points. There's 1 X-ray point we used, and these are the radio points. They're non-simultaneous, they're at different resolutions, hence a bit of a scatter. But you can do 2 exercises. You use the analytic ADAF model as a minimum. Say it's all from the ADAF, what would it look like? It could be consistent. Or you use a maximal jet model, and you say the rest is from the ADAF. So here the green line is from the ADAF, and the blue line is from the jet. And this you would say then is a jet-dominated model, and this is the accretion flow-dominated model. And then you take something in between, or your 2 limits of what you'd expect with the EHT. How much of 230 gigahertz flux from the accretion inflow, and how much from the jet. And we're playing with different kinds of models. We have different template models of well-modeled jets, about 10 of them. M87 type versus Blazar type and versus some other low luminosity types. We can use that as a library to get an idea of the spread, or we are using BHCC most recently, which is from Sarah Markov and collaborators. It has a lot of parameters. We've minimized the most important ones, and we get templates out of that and kind of do this fitting process. And you can do this to a lot of these nearby galaxies with minimal data points, a hard X-ray point, a few radio points, and you start to get at least the spread of expected fluxes from at 230 gigahertz. You follow this up, you choose the best ones, the most promising ones, follow them up with ALMA ACA, for example, and confirm their 230 gigahertz flux, which gives you better confidence in your model, and then you can move on to the ngEHT. So this, I think, would really allow us to do this, at the level of any source that you want to try out. If it was detected by eROSITA, we could filter these down to the most promising ones for the ngEHT. Of course, we have to check if these models are realistic. We're using, remember, these analytic JET models and analytic ADAF models, but we compare them in many cases to some more detailed SED modeling, JET plus ADAF modeling done with true integration of the ADAF, with true integration of, and slightly better parameters on the JET. Here's just one example, 3998, where we're pretty much able to reproduce. We don't get the bumps, but we pretty much reproduce the fluxes quite well. So it seems to be working. I just show you an example. We're doing this on a lot, but we're still working on it. And so the idea then is, we run these models on every source that has data, and we also store the predicted fluxes, both from just a JET power law, plus the JET plus ADAF fitting with all of its uncertainties and spread. And so now the database is ready. We have to uniformize it a little bit. If all you want to do is explore parameters and create subsamples, that's very easy. As I said, it's kind of like Airbnb interface that we're building. Right now it's command line, but we're building up the Airbnb interface where you basically just filter by anything you want, MBH, Eddington ratios or luminosities, fluxes, whether they are VLBI detected or not, redshifts and distances, as Priya asked. And at each point, it kind of shows you, you can plot any parameter against any other and color a third parameter. And it'll show you how your objects are reducing. And when you kind of reach the level that you want, you just export all of these figures and FITS files of your sample list, and then continue to play with it for yourself. So you can retrieve your subsample, and then you move to post-processing if you want to. And here is what we're trying to build, where we don't have the broker. We have a lot of the models, but we have to, again, integrate it into, right now we bounce it around between three of us who are working on it, because each of us are using our notebooks. We've now got a central computer, and we're going to move it all together. So the user basically comes in with a source or sample. We recently exercised this with Sarah Markov, who gave us and so all we need is a set of names or positions. Sorry?
We lost you in between.
Don't say
And so basically, yeah, it goes into the database, and we get all of our basic database quantities. And there are sometimes missing data, of course. So we also generate a lot of Astro queries to the typical places, NED, SIMBAD, Hyperleda, SDSS, try to fix any missing data because the source might be new for us. And then it dumps back to the user all the basic data and figures of their sample, everything we could cross-match, and gives them the basic statistics about this. It then gets passed to the models. At this point, we have the SED model working with, which is the JET plus ADAF, all the targets with enough of data, a black hole mass, and one SED point will get a model fit, and then you'll get the model results also. The plan, which is still here, is it then goes to, because you now have some kind of an idea of how detectable your sources are, but you also want to go into observing. When we are down to these low fluxes, having a close by phaser is very important. But since we've ingested the calibrator database, it's very easy to find out how far you are from a phaser immediately instead of using the ALMA OT. And we plan to plug in, we talked with Aaron and Dominic briefly. There's the ngEHT which will actually then, simulate your observations. This is the part to be done. We will try to plug into to an exposure time calculator and to the ngEHT because, for example, if you have an estimate of your ADAF flux, you have an estimate of your JET flux, you could just scale an M87 ring and an M87 JET or some other kind of JET to the distance of your source and the brightness of your source, and then see what it would look like in a standard subarray, a standard EHT array or any subarray. and give you your results of the simulations observed. The part we also want to build, and I think it's very useful, but this is open to discussion, is a broker. Because having done all this, you might find that your object is not there, or many of your objects are missing things, which happens to us all a lot. Sometimes you're just missing a redshift, a black hole mass estimate, or you get a nice estimate of 230 gigahertz fluxes, but you need to confirm these. So you want to confirm compactness, maybe you want flux monitoring, check phasors, or do coordinated fringe tests. And the idea is that if you kind of mark this as a request, of course, there might be too many requests. We have to see how to do this. Users who have knowledge of this, maybe private data, unpublished data, would be free to input it. We, for example, have plans already. Foremost and Moons are large multi-object spectrographs that are coming online in Chile. They are not things you propose for in some sense. These are hugely multiplex fibers. So what you do is you provide a huge source list to the collaboration. And if they're observing that part of the sky and they have free fibers, they just plug those fibers onto your objects. And so you get your process spectra for free at some point when they point to your area of the sky. So we made our first source list for this, and we're in discussions with subgroups of these teams to actually just put it into their main target list. So in some sense, it's not asking for redshift for each source. It's just putting it into these large requests for large surveys, but it could be individual source requests. AC and SMA, as I mentioned, we're already writing these not large, 100 objects at a time proposals. It can be very efficient if you have a lot of sources clustered on the sky, because you reduce your overheads with ALMA. So at this point, we're just using about 10 minutes per source for an ACA proposal because of the clustering. And normally it's about 35 minutes per source. ALMA is not a survey instrument, but if you have a large enough sample, it becomes a survey instrument. And then, of course, there will be individual and collaboration projects. And so the idea of the brokers, this already exists. For example, the LSST has built all these platforms, brokers, they give you alerts. You're allowed to update things. And we could try to modify this. And I feel it's really, really important because the SWGs are just going to generate so many that we need to check. And of course, then as we do this, we update the main server, main database, so we don't have to queries the source. And every now and then we refresh the whole database. And so this was the part to open, and I'll go back to the previous slide. Right now, we are hiring a programmer just to uniform. While our database exists, it's running well. We need to uniformize it and optimize it because it's a lot of sparse data in our tables, and so we're considering how to make this quicker and optimize the current model codes. Which actually, when we run MC on it, or even basic model fitting, it does take some time. And we're in discussions with some of the LSST broker teams. I mentioned LSA because it was developed here locally to use their brokers as a base because they've done the whole GUI and they've done the whole database. We just need to change what's inside and modify a little bit of it, and we could have a fully running platform instead of building anything from scratch. They have many more things that we need, but actually most of it will serve for us. And upcoming, we want to solicit design requirements from all of you to know, what are the things that should be in this database? What are the things you'd like to query? How do you want a broker or not? Finalize any requirements and then implement it. We have some students working on this, plus we are funding to hire programmers. And so this is basically to let it all open to all of you to see what we need to do. And it also comes back to this, as we're doing these, as we're doing our fringe tests on the ngEHT, as we're doing our ICA fluxes, we're getting a better idea of where the whole universe sits, right, in fluxes. So a better idea of if we really want to resolve nearby black holes, what sensitivity we need, how good passive phasing should be, because it's fine to say that my sensitivity is 0.1 RMS, but can I still detect a 10 millijansky source? Because my passive phasing has to be good enough. The way to do our scheduling, snapshot capabilities, subarrays, then the part that I was mentioning, any ideas about the database design, any ideas about the broker design. If you're familiar with LSST brokers, there are about 6 of them, and there are other similar systems. If you have preferences of things that you think are really nice, we could try to follow that. And so that was it. I mean, this presentation I'll share with you later just has some extra supplementary material kind of to go through some of the other details of real names, some of the parameter space we're covering, what kind of black hole mass range, what kind of 230 gigahertz flux, what sort of black holes are in the sample, and so on. But that was basically what I wanted to come to, and I'll leave it on here and then stop sharing. And very open to questions. And I know anyway, we also have to move on to the general discussion led by Priya and Jose.
Thanks a lot, Neil. Thanks. Can you hear us, Neil? Neil, can you hear us?
Yeah.
Yeah. Okay. Yeah.
I can.
Right. Thanks a lot. I have a couple of questions, but are there any other questions for Neil? Yeah.
Yeah, I don't know if you can hear us in the audience, but does LSST generate black hole masses and other things, or you would be using their primary data products to generate those secondary data products?
Right. So when I mentioned LSST, it was not in any way to use the actual data. It's that they've developed this whole database structure which allows database, but it allows Astro queries. It allows you to run Python, your own Python programs on top of it. And it has kind of a broker where you can request things. It alerts you when something has updated. So it's the software framework I meant, but nothing to do with the actual content of the LSST database. It's just the software framework that they've built up can easily repeat a lot of this. And we'd have to program very little bit additional. But the actual data that they do, of course, they're doing this repetitive imaging. And so they use it for very different purposes. And the only place where the LSST will really matter a lot to us is probably, I mean, there are many, sorry, I should say one of the places where I'm excited is all of the periodic oscillations of quasars, which will give us supermassive binary candidates. Unfortunately, there we looked into SED modeling them, and it's very complicated because you have the two accretion disks, you have the circumbinary accretion disk, and with the bright quasars, I think it'll be difficult. But I meant only the software framework without actual content of LSST.
Super, thank you.
Okay, any more comments, questions? Neil, during today's presentations and yesterday, we were discussing the relevance of having this list of targets for the ngEHT. So I know that Michael is trying to put together a number of people to lead like a tiger team to advance a little bit on this and so on. So I think we will hear soon from Michael and Shep about this. Okay, and but I also wanted to talk to you about. I mean, do you have? Can you give just a brief summary of the current observations you are performing to check the fluxes, the observations from the HT, so people can be a little bit aware of what has been already observed and tested, and timeline for. I mean, it could be just a matter of luck, and then we find one or two extra good targets, or do you have an idea? And this is going to take 1 year of 5.
So I actually, thanks, Jose. This is a very relevant question, especially since our EHT run is a month before the ALMA deadline, which creates this huge lag of getting to know our results before we propose for more. So to give you an example and where we can make ourselves more efficient. So in March 2022, we requested EHT plus ALMA fringe tests on 8 sources, which are effectively, if I draw a circle over here on this figure, I'm still sharing. So these are larger than about 3 to 5 microarc second in their ring size. And we asked for EHT tests here, of which 5 were observed, because the others, it turned out, have, the SMA team was very, very, very efficient in this and coordinating with Venki. They checked the fluxes of these sources just before the run, and a couple of them were too weak. And when this was done in March, Venki and the people at the bond calibrator managed to transfer a small amount of data from Pico and NOEMA to the bond correlator to try fringe tests of what we observed. And it turned out, for example, for NGC 4261, which is this one here, which is pretty decent in shadow size, turned out to be very bright. It was detected very, very strongly. And that was the only justification we could use 1 month later when proposing to do EHT imaging of this source. And if we didn't have that little quick, I don't even know if it'll be enough because it's a 1,000-kilometer baseline. So it's not so convincing. We didn't have a flux. All we could say is that there was a fringe on a 1,000-kilometer baseline, which was signal to noise greater than 9. And so this is one of the things that causes a problem for us, that we'll know their fluxes about a year later, just in time for like a 2-year later ALMA deadline. So basically your fringe test takes 2 years and then you ask for imaging. And so unfortunately, we're talking about a 4-year time scale. But if we could do quick FTP, during a run, if we could do quick FTPs of 20 seconds of data on each source, it would be really, really helpful to then produce the following proposal and cut the overhead by factor 2. So, but on the other part of the question, so what we already have in hand is fringe tests on 5 sources here, EHT fringe tests. 4261, as I mentioned, on that one baseline seemed to be strongly detected. The others had fringes, but it was not so convincing. They were maybe signal to noise 6. If Venki's on the call, he'll know better. Then we've re-proposed for a larger subset here, going deeper for EHT plus ALMA fringe tests this cycle. The results will be out next month. So in some sense, EHT fringe tests of this area is kind of done. EHT fringe tests of this area have been proposed, and GMVA plus ALMA imaging of these sources have been proposed at 86 gigahertz. So at this point, we've kind of reached, if I had to put a circle around here, if our proposals are approved, we would have reached EHT fringe tests of mainly all of these sources here, and GMVA plus ALMA imaging of these. Now, of course, the ones in blue are already, well, they haven't been imaged, sorry. The ones in blue have already been detected with the GMVA, but not necessarily imaged. It could have been just a snapshot. What we also are doing in parallel is what I showed here, these yellow sources, which are the very large rings, but very weak. Here we've proposed for all of these, and we have the data. As I said, they're kind of disappointing. Many are non-detections, and the most we get, 10 millijansky, is exciting, is a high flux, and we've proposed for the rest of them.
Neil,
so at least on
Neil, this target in yellow, just to remind everybody, the fluxes you put there are basically arbitrary. You don't know exactly the
yeah. I've just pushed them up to see where they sit on the x-axis. Thanks, Jose. Yes, the y-axis is completely arbitrary.
Yeah, we
could be lucky. And so here, I mean, any of these that come out, I mean, I'm just showing we haven't even gone down to 9 microarc seconds. So they're a very large number, as you see in the histogram here. It depends on how deep you want to go and how here. It depends on how much you think would be exciting. Now, even here, jet bases are exciting, and maybe super resolution if it's bright enough. But of course, the signal to noise is on a 20 or 50 millijansky source is not going to be high. But if we invest enough time, any of these sources could be interesting. So yeah, it's a lottery. If one of them turns out, or if monitoring shows one of them to change. And this has happened quite dramatically in several of the other sources. We know that there's a lot of variability. I mean, Jeff has been monitoring, Jeff Bowers and his group have been monitoring some of these. There's a huge amount of variability. A tip, which is either accretion in flow, or in many cases, what we know very well, new jet components coming out or disappearing.
We are losing you.
Love to do these. That would be incredible.
We lost you for a second, Neil.
But again, I think
Oops.
So yeah, I'll turn off my video only to stabilize the sound and start again here. And so as I said, basically we are playing the lottery, and let's see the ACA again. We'll know the results in March, and we need to talk to Jeff Bauer and every people at BHI to set up a SMA proposal. Where Danya and I is now preparing the lists, and we need to coordinate with them, and also for NOEMA to do some of these sources in the north, either because they're too far north to be seen by ALMA, or in some cases there's also an overlap where it could be easier to do it with SMA in certain cases. But really the most promising one, from the ngEHT point of view, I think the most promising one is this hard X-ray plus models, because that's really going to reach any given source that you bring up for your specific science. And because these other ones are just not going to reach that much. We have 15K sources here. We have hundreds of, maybe up to 1,000 sources here. But here we could access any given source that you query in our database. We could really try to make some kind of an estimation of its flux, and then test the best sources with ACA proposals.
Thanks a lot, Neil. Comments and questions?
Might be a first question, but how was these black holes of this yellow sources estimated? It was using the spectra or what is there in the source of black hole measure?
Yeah. Neil, did you hear Svetlana?
No, she was very far away, and so there was some echo. Could you repeat it? Because you're closer to the mouth.
I will repeat it for you. So Svetlana was asking, how did you determine the masses of the black holes that you plotted in yellow? That we don't know exactly what would be the correlated flux or the actual the total flux of the sources. Were they estimated from the spectra, from the IDAF modeling, or?
No, so the black holes come from, the actual black holes, and we as you know, there are very few measurements, right? So a lot of them come from M sigma, from the velocity dispersion of the bulge or the luminosity of the bulge, also called single epoch reverberation mapping, which is the width of a broad line, a broad optical emission line, H alpha or H beta or something in the UV, together with a continuum luminosity. But if you go to this specific one, the yellow figures, it's not so obvious, but the circles, which are all of these, the circles are actually true black hole mass measurements. So these are very reliable. These tend to be the low redshift sample. They tend to be very nearby well-known galaxies, and they actually have black hole mass measurements. The triangles, and that's generally true for all of the plot. Every circle is a black hole mass measurement, so you can actually trust its position here and the x-axis. Every triangle is a black hole mass estimation, and this could be from varying methods, and that's why I haven't even put error bars on them to not confuse the plot. These could move around quite a bit. So these triangles here tend to be from M sigma and from fundamental plane estimations using SDSS data. So these, yes, are highly uncertain and could move around by factor of 2, and I wouldn't be surprised. But the circles here have well-defined errors and won't move around. For the y-axis flux, again, as Jose reminded us, it's completely arbitrary at this point. And in many cases, it's not been measured, but that's what we'll be doing now. Of course, if you measure it with the ACA, that's a 5 arcsecond resolution. And so we have some kind of a global flux for the galaxy. We'll have to follow it up with the ALMA 12-meter array, which, remember, can reach 30 milliarcseconds, and will give you a good idea of what the true flux is, the really compact fluxes. And then we could do, maybe try a fringe test with the EHT. So thanks, Svetlana.
Thank you.
Thanks, Neil. Neil, another question. You had the sample for the binaries. Are you checking some of the fluxes for those sources, or what is the situation with the binaries?
Yes. So there are two. I would say there are two types. One is the figure I showed was just an illustrative thing of everybody, not just suspected binaries. This is just to show what's our linear resolution at any given source, which we know is a VLBI detection and which we expect to have actually I've gone down to 1 millijansky just to kind of show things. One could imagine that anything above something here, we could detect them. But in real, so there's about a sample of 300 to 400 posited binary supermassive black holes. This comes from, this is starting from your favorite OJ, Jose, and some of the VLBI direct detections of binaries, but a lot of them are because of periodic oscillations. In that case, what we do is, I probably have an example here, but this is an old example. Let's see, here's one. It's just an illustrative thing, right? So here's 0402 plus 379. where this is not a hard binary. It's a 7.3 parsec separation between these two centimeter wave VLBI cores, right? And so you can kind of, what we're doing is just a maximization of probability. We have an X-ray flux for the whole system. We have 2 radio fluxes for each individual core. And what they do present is that they think that the total mass is so much, right? So we have the total mass, but we have to kind of start to consider different mass binaries, different mass ratios. And so one could imagine that one of them is the dominant one, a high mass ratio, and all of the X-ray flux comes from it. So here's the X-ray flux measurement in the green point, if you can see it. And we just put in, we know the total black hole mass. We give it all to one of the black holes. We give all the X-ray flux to one of the black holes. And we say, okay, how much would the radio flux be in this case, based on this quick analytic ADAF model, and assuming that the X-ray flux all came from the ADAF. And you say, okay, I say DOM because this is Dominic's model. The expected flux is 40, I cut it off, but this is millijanskis here. We'd expect 40 millijanskis. And then you can take other cases where you divide them to get an equal mass black hole. So your black hole mass changes in the analytic model. You assign, I forget how much of flux, let's see, 6. Oh, you assign all of the flux to one black hole, but you say that that black hole is an equal mass binary, and you get 9 millijanskis. And you just statistically go through different mass ratios and different X-ray flux divisions, and you get a probability plot of what could be the 230 gigahertz flux from each. So I would say this, for example, is really worth following up. I've just shown the illustrative models here, but if you do it statistically, there's a good chance that one of them is detectable with the EHT. It's of course not the most interesting because it's a large separation. Here's another example, which is terrible though. 7674 or Markarian 533, there are these 2 centimeter wave sources found, and they posit that it's a potential 0.35 parsec binary. This would be very interesting for us, right? They give us an estimate of the total.
We have lost you, Neil.
And you can do the same exercise. There's also an X-ray flux for this. Actually, there are many more set points. Sorry.
No, it's okay. Go ahead. Go ahead.
Let's see. Let me start again. So here, is it better now? So here's
Yes.
7674. And once more, this is a more interesting binary because it's come down to the sub-parsec level. There are 2 VLBI cores. There's an X-ray flux. Again, just 2 illustrative models of assuming all of the flux in one of the black holes. And then we divide an equal mass binary versus a very unequal mass binary. And you can predict your 230 gigahertz fluxes based on a simple ADAF model. And it's down in the microjansky level. This is one example, but again, you can do it statistically. Different mass ratios for the binary and different X-ray flux divisions between the binary. And in general, it's not going to be very promising. These would anyway, we are going to put them into the ACA queue to find a true flux, just in case we've got it wrong. But it's again, just to illustrate that for these 300 real binary, 300 posited supermassive black hole binaries, we're doing this exercise of trying to figure out which are the best ones to follow up. And in the case of the VLBI detected ones, it's actually it's simpler because we can kind of assume maybe that they are ADAF dominated. In the case of the periodic oscillation quasars, it's probably completely unrealistic to claim it's ADAFs because these are luminous sources. And so there are lots of other models we need to use, which is from the emission from the disks, and it becomes much more complicated. We're trying to look into this now, and if anyone has experience, it would be very useful to try and see if we can estimate 230 gigahertz fluxes based on their SEDs in some other kind of said modeling way to get a 230 gigahertz flux.
Neil, sorry, how do you know this C1, C2 is 2 cores, but not a core and some core?
So it's been some time since I read this CARB paper. So let me, this is 15 gigahertz VLBI 0.8.7. If I remember right, they had multi-frequency data and they found both to be I'm sorry, Svetlana, I don't remember the details of the other parallel observations they had, the other VLBI observations, which made them think that these are two flat spectrum cores, and therefore in potentially a binary supermassive rather than a component in a jet or something else. But I don't remember the details. I'll look it up.
But Neil, you mentioned that these are bona fide binaries. I mean, is this based on optical spectra or?
No, in this case, this is because they are VLBI resolved compact cores.
Okay.
But there are very few cases. We're talking about maybe 10 to 15 cases of VLBI resolved multiple SMBHs. The bulk of the sample we're studying, which is these posited binary SMBHs, come from variability studies or jet precession. There's several other things that come in. And so it's something we've started. We've started to model the VLBI resolved ones, but we're having trouble modeling the bright quasars with periodic oscillations, modeling in the sense of trying to estimate a 230 gigahertz flux. So that's very much in process and part of a master's thesis of one of the students here, Joaquin Hernandez, but only now starting. And LSST, I think, will give us many more of these sources. But again, there'll be these relatively bright quasars where we can't really slap an ADAF and jet model on them. And we're talking to people here, to simulators who do these kinds of binaries, the brighter binaries. Right now, the models are difficult. The set modeling is difficult, and we don't have enough data points to actually go in there, put in all those free parameters and still get an estimation of the 230 gigahertz flux. So what we plan to do at this point is just empirically follow up some of them to try and understand them better. I'm sorry, follow up meaning direct 230 gigahertz measurements of some of these sources.
Paper came out last month on this source challenging the binary black hole.
I'm sorry, Jose, could you repeat it again, because there was echo from far away?
Can I repeat it if you want? Yeah, no, go ahead.
Yeah, so Neil, a paper just came out last month challenging the dual AGN interpretation of this source.
Yes. Yeah, yes. So no, I agree. I agree. Again, this is I'm showing it as an illustrative example of what we're doing with these, and I agree. Many of them are weak justifications. Having said that, maybe I'm not thinking of this. Let me look up that paper. Then I've probably missed it. I'm thinking of a couple of others. I'm starting to get mixed up between the 10 to 15 sources we're working on, where the evidence is weak. Yes, but I'll look this up. Then thanks for the comment.
Thanks a lot, Neil. Any further comments, questions? I think we only have 10 minutes left. Okay, so summarizing, Neil, I mean, this looks really nice. And as we started from the beginning, the idea is to have a dedicated focus team working on this and trying to find the best candidates, and we are going to move this forward and with very high priority. So this looks great. Yeah, Selena, you want to comment?
I think that we need some kind of very small amount, 3, 5, very strong benefits. So that it is really important, or even about 1, 2 new, which kind of is very good determining fluxes, black hole masses, and so on, which can be a new target for energy.
Did you hear that, Neil?
No, once more with a lot of echo. Sorry, Svetlana is quite far away.
I will repeat it. Yes, Svetlana mentioned that, yeah, it would be really nice to have it, to have this, at least even if it is just a handful of possible targets, so we can try to refine a little bit the science that we could do and whether we'll be able to get some of these estimations that we want to do about the spin and the masses and so on.
Yes, so that they
Yes.
have also very well measured X-ray. They would have a good optical spectra or something, so that it would be possible to concentrate, for example.
Yeah, that sounds good.
Right.
Yes. Yeah, do you want to comment on that?
No, I agree. I agree that, I mean, there's some, let's see how much we can integrate in, because I mean, of course, we're still quite limited in people power, but I understand the point, as a lot of these reliability checks plus the ingestion, it does take time, and we'll try to automatize it as much as possible so we can, plus we do cross checks, of course, between different methods. As you imagine, building up this very large database, you have many black hole masses that are estimated by up to 4 methods. And we do these cross checks, but at this point, we're not doing any systematic corrections, but we're keeping reliability flags, we're keeping errors. But at this point, we haven't tried to ingest time variability or spectra, because that's kind of complicated, but we need to look into this. But we can definitely filter it down to the most reliable subsample. And of course, this is freely available. I mean, we would love it if you wanted to exercise the database and send us any source list you want, and we can send you the output. And we'll try to make this, we're cleaning it up right now a little bit, and we'll try to make it in that sense freely accessible as quickly as possible. So you could go in there and just download the whole database, or search it with our and run the models, do everything as far down the pipeline as we have got, which is minus the ETC and EHTM and minus the broker at this point.
Thanks, Neil. Actually, we will have to close it like in 5 minutes. Yuri was supposed to give also a presentation, but I'm afraid that I have been checking whether he was connected or not. He may have got to the time wrong or something, but I don't see him here. So he was going to talk about the connection with neutrinos and how the paper is going and the white paper is going and so on. Other than that, I mean, this is also,
Yes, another white paper that is being prepared. We have discussed in one of the meetings of the platform conference group is by Jiang on the possibility of applying source frequency-based referencing with the ngEHT. Of course, he cannot come here because of lockdown. Yeah, he asked me to briefly mention the current status. We also don't have slides prepared, but anyways, we've been discussing with the writing team on the contents of the white paper, and now slowly filling in the contents. Just a brief recap. We're gonna this white paper. We're gonna include talk about the possibilities of applying frequency-based transfer and source frequency-based reference, and with the ngEHT, and especially the enabling the astrometric capability will allow us to, for example, possibly detect the core shift of the second star, or determining the location of the black hole in MT7, and suggest we see that longer wavelengths. I think in the meeting we are mainly discussing in the future, if we improve the dynamic range, we will be able to see the shadow and the jet at the same time. But anyway, the jet components, they are optically thin. So at 1 millimeter, they are always quite deep. So an alternative way to determine how these were collocated is through the astrometry, which is possible through source frequency-based reference. And after the discussion with Richard and Maria, we are now also adding things like with frequency-based transfer, we can extend the coherence time, and then this will enable us to detect more weaker sources.
That's the point.
Has been talking about this.
Yeah. Yeah, that's an excellent point, Juan Yao. I think that the possibility of detecting weaker sources, I mean, it could be extremely interesting here. Yeah. And do you have an idea? I mean, how much we can? I mean, we're talking about detecting what millijansky, sub-millijansky.
I don't have the exact number here, but I think Richard and Maria has checked the estimated coherence time and sensitivity. Jiangmu is actually estimating the number of sources. So really include this in the paper notes. I don't have the number now.
Okay, so we will discuss this. Hey, Angelo, your white papers are progressing really nicely, no? Yes. Can you comment on this? Or?
Sure. I actually did a talk with the Just Nutrition call, just not call, room just before the coffee break. So there's one white paper coordinating about black hole spins, why we care, and the ngEHT's role in this area. We're going to talk a little bit about the cosmological evolution of black holes, and then some potential ways in which we can extract spin from photon rings, as well as long variability of moving structures. And oh yeah, if you're on the page, there's a green link that you can click on.
For me.
And polarization patterns. But yeah, so that's going all fine. And the other one is more related to accretion and calorimetry. Today. Been working most closely with Michael Johnson, and we're talking about this. And you can look at the they're both edit and remix in this document.
Great, wonderful. Then it's Velana, Rocco. Do you want to comment on the multi-wavelengths? Oh, by the way, we have Matt here, so it would be really nice to discuss this, because as you know, Matt, some of the for this theme, there could be some overlapping with the jet formation, especially what deals with the innermost jet regions with the collimation, acceleration, not the actual formation, but rather the acceleration and collimation and so on. And of course, it has also the component of multi-wavelength, high energy emission, and neutrinos, and that kind of things. So yeah, please go ahead.
We can actually be discussing that. So fuse cosmology is one of the most relevant studies of black hole and jets. So we actually covered several aspects, including these jet connections, the nature of the core, as I say, presented this morning. And we have a draft, at least, of the general paper about the synergies with the other multi-element facilities, plus the one that Priya mentioned is one of the series of this paper. And yeah, I mean, we presented something already during the last call of the group, and we soon share the drafts of this paper.
Yeah, Matt, it would be nice if at some point you could join one of our calls. I regularly join also your calls, but at some point it would be nice.
Yeah, I have to ask the schedule.
Perfect, wonderful. Yes, yes.
What's the relationship between the paper you're talking about and the covalent Bobbin one? Like, because they're both talking about multi-messenger, multi-wave.
Yes.
Yeah, but Judy is more about neutrinos, neutrino connection, neutrinos.
Okay, so neutrinos is not in the
So in our paper, we're trying to make a general overview, and then a few topics. There will be dedicated web papers for specific topics like neutrinos, like neutrinos by number, and polarization.
Yeah, this paper about neutrino, this quite advanced also. So this is.
What is the plan for that? I mean, what's in that paper? Do you know?
Yeah, the idea is to try to determine what is the acceleration mechanism for the protons to produce a neutrino, and to have a triggering opportunity for the ngEHT, and to try to see the sources for which we have some connection. I mean, how we can actually try to determine whether there is something in the jet that we see that is flaring and that may be connected with the neutrino.
I mean, this also sounds like it has also a lot of overlap with this sample finding project that, was sort of tasked to us. I mean, at some point we should discuss.
Who's it?
Because, I mean, basically, like, the cross samplers being the deal, right?
Yes.
To try to find out which ones are going to be co-observed with CTA.
Yes.
These will also be.
Of course, yeah, nice, of course.
Maybe make sure that we're like all.
Absolutely, yes, nice, yes. Yeah, something what we have discussed. I mean, if for this team, I think there should be basically some of the people we are here, you and Matt, I'll be there, and of course Neil and other people. Yeah, definitely we should coordinate this. Yeah. All right. Yes, I think we need to close it. I mean, there are some white papers about the connection with multi-wavelengths, but Roman is not here, and so on. So and actually, yes, we are over the hour, and there is going to be a tutorial starting at 6, and we still have to announce an update. All right. So I think this is it for today, and just a reminder of the program. There's going to be
Here.
What do we have now?
Second look. I think now we have the poster session, the lightning. The tutorial
Yes.
is cancelled because.
Yeah.
A second, let me stop sharing. Let me stop
No, but then
recording.